All right, so we have Surya today telling us about topological quantum computing. So take it away, Surya.
Awesome. So it's going to be a pretty short kind of talk. I'm just going to give you like an introduction to the idea of topological quantum computing, some of the, maybe one example that gives you an idea of how they do it and what it's supposed to mean, and kind of basically enough pop science for you to do actual science if you're interested in that. That's the idea. So in topological quantum computing, there are three like main pillars on which it stands. Topology, one, quantum indistinguishability, which is two, and there's something called anion braiding. And so we're going to see what that is. And these are the three main things that kind of it builds on. So let's go into quantum indistinguishability. So in quantum mechanics, every particle of a particular type are exactly the same. So you can't label electrons or you can't label protons. All electrons are exactly the same. They have the exact same charge, mass, of other properties. And so when you in such a situation, you always have to talk in a statistical way. Yeah, it's like a bunch of electrons. What is their overall behavior? You can't say electron 1, electron 2, electron 3. There is no individual electron characteristics. And so one really interesting thing was Wolfgang Pauli. He showed that this particle indistinguishability is somehow related to spin of the particle, even though spin is an intrinsic one particle property. Like a single electron can have spin. It's not a statistical quantity, but somehow spin is related to how the statistics of a particular type of particle behaves. For example, he showed that particles with spin half, the intrinsic spin of S equal to half, can be shown to have, they're called fermions, and they have fermionic statistics, which means two of them can't be in the same place, or two of them can't have the same quantum numbers. They kind of dislike being in the same position or the same quantum number state. Whereas particles with integer spins called bosons, they don't have problems like that. They are like, yeah, we are going to hang out together on the same state, and we're totally fine with that. This was such a non-intuitive idea when I thought about it that way. I've done quantum indistinguishability before, and I've done this spin-based stuff before also. But to think about it, spin is an intrinsic thing. How is that related to its overall behavior? And why is it like a one-to-one almost mapping? That's pretty interesting. And another thing which I found out when I was trying to make stuff to talk about is that this quantum indistinguishability depends on the number of dimensions you live in. And kind of very specifically depends on if the dimensionality is 2. If it's 1, we're fine. If it's 3 or above, we're fine. In 2, something is weird. And we're going to look at why that's the case. So let's take two particles. Okay. You have two particles, and what you want to think about is if you want to switch them around. All right. So switching two particles around can be thought of as you keep one particle fixed, you rotate one clockwise or counterclockwise about the other, and you move the whole system. Moving the system is almost trivial. It means nothing. It's just a shift of the axis. But this rotation could have an effect. And we can see that in 3D, it doesn't really have an effect, because anytime you want to rotate a particle around, you can always lift the particle onto another axis, kind of trivially move it around, and then place it down. So if you look at the diagram here, supposing these are your two particles, C0 and C2 are the same topologically, right? It's just a constant the path that the particle takes is just, you can just shrink it without tearing it, without doing anything. So C0 and the C0 path and the C2 path are exactly the same. The C1 path is different, but not really, because you can just lift the path continuously smoothly off the plane and then shrink it and then bring it back down. So in 3 dimensions, all 3 paths are exactly the same. Switching them does nothing. So you can see that mathematically, what it means is that e power 2i phi is 1. So phi is the angle of rotation. And so when you do a complete revolution, your phi has to be quantized in this particular way. The phase that you pick up, that your particle picks up, has to be either +1 or -1, pi or e power 0 or pi. And the two values gives you protons and gives you bosons and fermions. When you do a switch like this, if you get a plus sign, you get a boson. If you do a switch like this, you get a minus sign, you get a fermion. And that's all of particle statistics in 3D. Because you can just lift it out of the plane and continuously deform it and place it wherever you want. But in 2D, if you're restricted to a two-dimensional space, you can't lift it out of the plane. So going around is strictly different than not going around. Like C0 and C1, C2 and C1 are strictly different. You can have weird properties like this even in 3D if you have an infinite, like this is a very famous experiment, the Aronoff bomb effect, where you have a long tube of current passing through, but you're restricting in a superconductor, so you're restricting the magnetic field within that. So that is kind of, you're making sure that it has to go around or not around. There's no option of going out of the plane, around, and coming back down, right? So you can see this kind of phase effect that gets built up. In 1D, there's no question. In 1D, if you want to switch them, they have to go through each other. So it's always going to go through each other. So it's kind of trivial in that sense. 2D is the more you think about it, the weirder it is. Only 2 dimensions has this kind of problem. 3 dimensions, you avoid it, and higher dimensions, of course, you can just avoid the problem.
Can I make a comment really quick?
Yeah.
So this all boils down to the fundamental group of R2 with the point removed, not being trivial. Okay. Yeah. Are you with me, Roy?
What do you mean by trivial?
So when you take so if you remove a point from the plane and you take a loop that contains that point, it can't be shrunk to just a constant path or a constant loop, right? And so the fundamental group is not just the identity group. And in any higher order Euclidean space, you can just move your loop around and then shrink it, right? But it
that's
can't.
Exactly this is quite interesting.
Yeah. So wow, that is. So you're saying this has something to do with the distinction between bosons and fermions and other types of.
Yeah.
Wow, that's really cool.
So for the one-dimensional case, would you just rotate the axis without doing anything, or am I missing something?
No, in a one-dimensional case, all particles have to move along the same line. So if you want to swap them, they have to go through each other. There's no different way of doing it. That's why they call it trivial in a sense.
Okay. Yeah, like in 1D, there is no loop. There's only line.
So that's actually pretty interesting, Zach. That just that concept kind of leads to bosons, fermions, and in two-dimensional systems, exotic matter is what the kind of exotic phase is.
You're kind of blowing my mind right now. So continue.
So if we're stuck in, how do we create a system that's stuck in 2D if the real world is 3D, right? So I think we do it in quantum mechanics, we do it all the time, but then I'm just going to give you an idea of how to do it. If you create a potential supposing you create a Z potential, like a infinite square well, right? Like you have zero potential, but you have infinite potential once you cross Z less than 0, Z greater than A. What ends up happening is you create levels, right? Energy levels, like n square h square by 8 ml square. Those are the energy levels. And if you create the length that's either short enough or long enough, then you can create the gap between levels to be extremely high. So what ends up happening is your particle is kind of stuck on a particular level. And so you can essentially confine it to a really small Z delta. Like a delta in the Z is going to be really small, essentially making it a two-dimensional system. And that is exactly what they do. They create a trapping potential in 2D in the Z dimension, which is really strong. And so the particles are restricted to so the remainder of the wave function becomes a two-dimensional wave function. And so if you have, in the real world, obviously 3 dimensions. three spatial dimensions. But if you take any boson or fermion and you kind of restrict them like this to a two-dimensional subspace, then their exchange statistics start showing these anyonic behaviors. They're no longer bosonic switching or fermionic switching. You get these kind of topological behaviors once you can restrict them to a particular dimension.
So just to be clear, you use the word anion. So is anion the term used to describe that sort of like different parity in the switching that you were talking about on the previous slide?
Yeah. So any particle that doesn't have +1 or -1 when you switch it is considered an anion, because it literally ANYON, any-on, any phase. I think that was the idea behind the name. You can have any phase that's picked up. So if you look at it, any phi is possible. So these kind of bosons or fermions, group them up in a, like if you take two of them and you restrict them to two dimensions, their statistics is really different from the underlying boson or fermion statistics. Just like in superconductivity, if you have two fermions, but you pair them in a very specific way, they have boson statistics, right? Stuff like that. So these quasi particles that emerge from the real particles, when you group them up and you restrict their dimensionality, those are what we call anyons. So if you look, so this is about anyons and stuff, and how do they, so this doesn't seem like it's a computing thing. So where does computing come from, right? When you say topological quantum computing, what they do is the world lines of the anyons. Since we're restricting them to two dimensions, we can start talking about world lines as time goes on one of the axes. And so if you have two anyons, and then how you switch them, like if you do clockwise or counterclockwise, their phases can be different. And the phase is just a specific case of a general unitary, right? A phase is just a one-dimensional unitary. In general, you can show that for different particle types, you can have a general unitary that you can act on the initial space. And so by braiding these world lines, by switching them in very specific ways, you can create any particular unitary that you want. Well, I'll show you an example as we go along, but that's the basic idea. Why is it inherently more safe from errors? Is that switching a particle is like a continuous deformation. So even if there's slight noise and the trajectory gets kind of wonky, as long as the overall switch happens, it's always about it's independent of the path taken. It only depends on the final initial and final position. So if noise creates some wonkiness in the path, it doesn't matter, as long as when the final measurement happens, one is to the right or one is to the left, crude way of saying it. It's kind of safer from noise. So the kind of noise that comes in anyonic quantum computing is different. For example, the trapping potential, if it's not high enough, then it becomes kind of a 3D model, you're going to lose this anyonic behavior. That could be a source of noise. So those are different ways of getting noise, but this kind of switching is kind of inherently safe from noise. So if you look at computing with anyons, there are three or four main rules, just like we have the rules of quantum mechanics and how we talk about, Hilbert space. These are your gates. This is your measurement. These are post-measurement state, and you have those rules. Just like that, we have a set of rules for anyonic computing. So you have a set of particles, what you call the vacuum, or a boson, or a fermion, or an anion, or stuff like that. And you label the set of particles. Usually there's a one, which is a vacuum state, it's a very specific state, and then A, B, C, D, how many ever, and it's antiparticles, A bar, B bar, C bar, D bar. Some of the antiparticles could be the particles themselves. So the first thing you need is a labeling of the particles. And the next is how you fuse them or produce them. So if you look at this diagram, you can see that as time goes up, C kind of pair produces A and B, or A and A bar kind of fuse together, right? And A and B switch. These are the kind of operations that can happen. And you have rules for creating these. And so again, here you will notice that there's some implicit Einstein summation convention going on. So here it's written out explicitly, but usually they just write A cross B is NCABC, which is like if A is a particular type of particle and B is another type of particle in your space, what does fusing A and B give you? What are the possibilities is this expansion? So these are fusion rules that say bringing together, how do they behave collectively? So when I go down, you'll see an example of the Ising model, which is like the first model that I spoke about. So this rule will say that if you bring together two fermions, they will have boson statistics, stuff like that. That is kind of what this rule is supposed to say when you fuse them together. It's not, you should not think about it as actual fusing of the particles or particle antiparticle annihilation, anything like that. It's always about collective behavior. It could just be you put both of them in one box, and how does the box behave now? That could be considered fusing, right? So this is fusion. So we talked about types of particles. You got to label all your particles and antiparticles. The second one is how you fuse them. The fusion rules, they always come in this form. They're called the F matrices. So every system you propose, all you have to give them is these are the types of particles. These are the F matrices, and these are the R matrices. And we'll see what R matrices are. Once you give those three things, your entire system is kind of well described. So if you want to convert from one particular world line diagram to another one, you got to use the F matrices. That's the way to think about the F matrices. And the R matrices are, how do you switch them? If you braid, like if you swap the particles A and B, or if it's essentially called you braid the world lines together, you get a matrix times the unbraided version. So this matrix is the unitary matrix that we think about in traditional quantum computing. So we create whatever unitary matrix we want, and supposing we want a Hadamard, then we say, I want these two particles to have such behavior that when I switch them or when I braid them, I get a Hadamard on the input state, stuff like that. So as a summary, this is how you create it, right? If you have state initialization, like the all zero state or whatever, in the anyonic case, you just create them and you arrange them in a specific way. You want to do a particular quantum gate, like control knot or Hadamard, then you braid the anyons in a specific way such that the overall final state is U times the initial state for whatever U you want. And when you measure in classical quantum computation, in topological quantum computation, what you do is kind of you merge two of them and you see the outcome, and you can figure out the anyonic charge.
Is classical quantum computation what they call it in all the resources you read? Because
no, I don't.
Okay, I was like, I'm gonna kill whoever came up with that, but never mind.
That's me. The person you need to kill is me.
Please no murder in the group.
But so, like, I think I understood really all of this stuff once I looked at an example. So Ising anyons is like the simplest example that they talk about a lot. So you have three types of particles. Remember, I said you got to label your particles. You have three of them. You have a vacuum, which is one, a non-abelian particle, which is sigma, and a fermion, psi. And they give you these fusion rules. The first fusion rule signifies if you bring two anyons together, these non-abelian particles, they might annihilate and give you the vacuum state, or they might give you a fermion. So that's why it's one plus this. If you bring an anion and a fermion, it always gives you an anion. And absorption, like there's no change in the anionic charge in this case, and two fermions always gives you the vacuum state. This is a particular system. It's not true for any system. You got to create your own rules, but this is true for the Ising system. And so what would computation look like? So the circuit diagrams that we're used to, which is left to right, and you have the input state and your gates, this is what a circuit diagram looks like in topological quantum computing. You start with three vacuum states and a fermion, and you arrange them in a particular way. And then these are the pair production. So you do the braiding of the word lines, and then you do the fusing and measurement, and you get some particular state. So this you can think of as psi gets copied 3 times. That was the example that was given in the document that I was reading. So it's not really copying because, again, they have their own no cloning rules and they have their own set of rules. But this was a way of saying fermionic behavior can be made to move across this. And this is a very specific one-dimensional phase kind of braiding. But you can have different braiding with general unitaries, and then you would get an output state, which is like U times the input state. And you can measure it and you can figure it out. Again, what really makes this interesting is that this braiding thing that happened here, that is noise resilient in a sense. You can braid it in the weirdest possible ways. You can take it to the moon and bring it back and go around or something like that. As long as the initial state and final state are just switched, that's going to give you the correct answer. So noise can affect your switching process, but it can't change the outcome. Which is why I think Microsoft is really like, yeah, this is the way to do it. If you can create one qubit using topological quantum computing, then we are already miles ahead of companies that can create 10 or 20 noiseless, 10 or 20 current qubits with noise correction and stuff like that. So this is kind of where I stopped. This is kind of what I understood, but the idea was that this seems pretty dang interesting, and it all kind of boils down to this initial idea of, can you get off the plane or are you stuck on the plane? And that is awesome.
Do you have what resource you were using? Could you?
Yes,
share it?
I'm going to send that. It's a 200-page document. I'm going to send that. You guys should definitely read it.
Because it seems really cool.
Yeah.
This is awesome.
Can you also post it on Discord as well? Would be great.
Yeah, I'm going to post it.
So I'm just wondering, like, so they kept saying, well, the problem is that that these anyons don't exist in nature, right? That was always the critique against topological quantum computing, as anything more than like a tool to draw diagrams. But it seems like, well, then the problem is that you haven't constrained them to 2D well enough, right? It seems like that's what you're saying is the issue, is your track is just not good enough.
So they've created more sophisticated models that have greater theoretical properties like Majorana fermions and Majorana modes and stuff like that. But I honestly, in my opinion, I don't think it's an engineering problem at this point. I think you can create good enough one-dimensional traps. I think like it's possible, and it looks like Microsoft is saying is exactly the same thing. It's just we got to find out more and more creative, clever ways to restrict these particles to 2 dimensions, and whether we can actually do this switching without them leaking out to higher dimensions. That's kind of like the problem. Theoretically, this makes sense. The model works. Now it's an engineering problem, right?
Marguerite, are you thinking what I'm thinking about the equivalence between this and the gate model?
Yeah, possibly.
Tensor networks.
Yeah, so to clue in the other 2 people on the call, so we had been looking at like a tensor network like relationship. So you have these like tests that you can like evaluate your traces by doing some tensor networks shenanigans, and you can get acceptance probabilities by doing this. And for this one particular set of tests, Zach was able to equate it to like cycle index polynomials. And then there was a question like, well, when you do a trace in a tensor network, you take the outputs and you just feed them back into the inputs. Well, that looks a lot like a knot. Right. And so we were wondering if there were if we could say anything about like knot invariance and things like that based on these sort of tensor network drawings. But it's way more apparent, I think, in this formalism, because everything is knots and braids and just naturally.
Yeah.
Let me find the document before I forget to upload it. It should be on my desktop.
Okay. Note that you're still sharing your screen. I don't know if you care about that.
Oh, am I still sharing my screen? Okay.
Yeah, and we're also still recording.
Yeah. I have another point. So this all came down to the fundamental group of the plane not being trivial, and there are other surfaces for which that's true. And I'm kind of wondering if, we can do some kind of topological quantum computing, where the fundamental property is just that these other surfaces are not, they don't have a trivial fundamental group.
Right.
But I don't know. That's something to think about, I guess.
Yeah, I think,
The
like in
torus,
my
for example.
opinion, I think it is way more likely for a mathematician or someone with a good mathematical foundation to get into topological quantum computing, because once you get the idea of the physics behind it is, yeah, you switch to particles, they're going to have a phase, and then but it's all group theory after that, group theory and topology. So it's really hardcore mathematics.
Yeah, I mean, the head of Microsoft's quantum computing research, I believe, is a mathematician.
Yeah.
Yeah.
All right,
Makes sense.
that's good to know. Maybe I'll be working with Jeremy one day. All right, I'll stop the recording.